Hello guys, today we'll be talking about a very important topic that you might have all heard of, and it is called transformers. So you all have heard of, if you are aware of NLP, NLP have made a very big strides after 2017. I'll tell you later what happened exactly in 2017, but by till 2017 there was certain models, deep learning techniques in order to solve any of the NLP problem, what more precisely calling it as for processing text basically in order to determine the relationship between or understanding the words. So the deep learning methods that were available at that time before 2017 were like RNNs or LSTMs, and also some people used to use GRE. I hope you all know the meanings of these terms. However, these are not very important in understanding transformers as these are completely discarded in the transformers, and it's not transformer doesn't even touch upon these topics. That is, these were totally termed as redundant after the introduction to transformers. So exactly in 2017, Google Brain came up with a new paper, and the title of the paper was "Attention is all you need," and the title was very accurate. That is, attention is all you need. In order to solve any of the NLP problem, the only thing we need to do is to apply attention on the token. We'll be diving deep into what is attention, why the title is this, and what does the transformer really means. But so let's talk about a bit on RNNs, LSTMs, and GRUs. What these used to do basically before this even this transformer network came into picture. So the task of these certain models was basically understanding the tokens, okay, in the recurrent functions. So we know that if there is a certain word, let's say cat, and if we feed this word into a word to vec, okay, what does this word to vec do? This is in Gensim library. You can go and check it. So if you feed this word to vec and try to generate a vector out of it, it will give a vector, okay, of certain length. Okay, so this vector is actually a representation of this whole word in a numerical format. Okay, so there's a certain vocabulary in this word to vec. So it's basically this word to vec is basically um, takes text as input. So let's say how does even this vocabulary work? So let's take a very simple example. Let's say we have a words like a, a, or Aaron, and up till Zen. Okay. So this whole vocabulary, let's say these are the words in the whole vocabulary, and let's say the total length of these words is 10,000. Okay. So if you are supposed to generate a vocabulary out of this, how would you do this? You'll simply take this and you'll create a vector, a matrix. Okay. And this matrix will basically, let's say it's a one hot encoded matrix. So let's say it starts with A and then A and then Aaron and then so on up till Sid. So this will for this, and this is the length of this whole matrix is 10,000. Okay, and so this for this one, A is here, so it will start with 1, and rest all the terms would be 0. For AA, it will start with 0, this will be 1, and rest all will be 0. Similarly, right? And for Z, it would be all 0, and only the last term would be 1. So this is a very simple format of generating a dictionary for a vocabulary of for a vocabulary of say 1000, how do you convert it into vectorization? So this is basically a vectorization. Okay. However, there are other things as well. So suppose there are certain words which are not in this vocabulary, so that you can even add certain tokens for that. So let's say you added one more token. Let's say the token was UNK, which stands for unknown. So then your length, then your matrix will become 10,001. So this all will be zero, and here there will be one more zero, and this would be one. So this would be 10,001 cross 10,001. Okay. So this is a very basic kind of a vectorization technique. Now let's say you want to vectorize it, and but you also want that there should be a certain understanding to it. So if we see there's no relationship between Aaron, and let's say here there's a word called cat, and there is a word tiger, and then there is a word dog. We know that tiger and cat, they belong to the cat family, right? So there should be a certain similarity between these two words, and that should be shown up, or that should be represented in their particular vectors. So in order to do that, word2vec is has developed a dictionary where all the words which are similar to a certain token would have certain sort of similar index, some sort similar vectorization. Even you can find the similarity using this GenSim library. Word2vec, you can find a similarity between the two words, and you'll get a similarity index also. So you can get to know what all words are similar and what are the words are different. Okay, so that's the whole idea of the vectorization. And why do we do vectorization basically? Because our neural networks takes only numbers as input. Okay, they can only learn from numbers, right? So that is why they take vector as input. So now coming back to RNNs, LSTMs, and GRUs. So basically, RNNs analyze the tokens in the recurrent factors. So what are the tokens that you have? So let's take any statement. Let's say the statement is the cat is sitting on the rug. Okay, the cat is sitting on the rug. Okay, let's consider this sentence. So what your RNN will do, it will take these tokens and it will try to understand the meaning underlying to this tokens. Okay, in a recurrent fashion. So this will be fed into an RNN. It will try to understand what these words mean. Okay, so let's not dive deep into how this exactly pans out. Let's now look into what would transformer do in this case. Okay, suppose this is your sentence and you want to feed it into a transformer and you want it to understand, or how does it even understand if you want to see it? What does it do at the very beginning? The first thing first, what it will do, it will convert these words into their vectors. Okay, vectorization. Okay, there would be vectors for each and every word. And if we talk about what does a transformer do, okay, in a very layman terms or very simple terms, we can simply say transformers are doing nothing but just mixing tokens. A very crude way of talking about what transformer really do. So how does it even do? Instead of understanding the meaning in these words and try to analyze these tokens in any form of recurrent fashion or anything, they would simply try to understand what is the relationship between each and every word. So if this is your sentence, this the cat is sitting on the rug. So let's say you are trying to do classification. So in the case of classification, we are using a bird model. So for it to start, you there's certain tags that you use. So it will start with CLS, which would tell the model that you need to classify it, and it would end with SEP, which means this is the separation between two sentences. Okay, so it will be like CLS The cat is sitting on the rug, and then SEP. And again, let's copy this here. CLS. The cat is sitting on the rug. Okay. CP. Now you want to now what would a transformer do? The transformer will simply try to find the relationship between these words. So it's so if I'm calling it words, it's basically tokens. It will try to find the relationship between all the pairs of tokens. That is, even the word itself. So the CLS will be tried out with all the words. Same goes for the with the itself, then with cat, then with is, then sitting, then on, then the, then rug, and then SCP. And similarly, it will happen for all these. Okay, I'm not drawing all the lines, but yeah, that's how it happens. So that's how the a transformer tries to learn the underlying, or let's say it tries to find the relationship between the tokens by understanding the relationship between each by finding what is the between every pair of tokens or every pair of words. It tries basically, let's say, what does it basically do? It does the dot product of the tokens. Okay, so this thing was introduced by Google Brain in 2017. And why is it called attention, right? So the whole idea of attention was to do away with the recurrent neural network. So there's no mentioning of RNNs or CNNs or even the neural networks. Neural network does come into picture, but not that much. But these traditional methods of uh, working on the NLP problems were not even talked about. Okay, so let's go to the transformer network. Let's try to look at it. How does even looks like? So the transformer network, the original transformer network, which was proposed in the paper "Attention is all you need," consists of a stack of 6 layers, and the output of layer L, let's say output of layer L is an input to layer L plus one, and there are 6 layers on the encoder stack. So there are two stacks, that is encoder and the decoder. So encoder stack is shown on the left side. If you I'll show you the diagram how it is how the transformer looks like. So encoder stack is on the left side and the decoder stack on the right side. So that's how it is. So let me draw the encoder stack. Okay. So let's say these are the inputs. So there would be embeddings generated from it, input embeddings. Then these embeddings, I'll explain you what does this mean. It's basically positional encoding. Okay. And why this is represented by a symbol like this. This is basically sine wave and cos wave. I'll let you know why it's shown like this. And it's a very interesting method if you understand it, how they exact do the positional encoding. That is how they tell the transformer network where the word lies in a sentence. So that's what is positional encoding. And then this gets fed into an encoder stack. Okay, so let's draw this. So this input embedding and position encoding only happens once. So this is the, and then comes the stack of 6 layer stack of this particular thing which I'm going to draw. So this thing will go into an algorithm called as multi-head attention. And there are generally 8 heads. I'll draw 3 lines for this. Okay. And then this would be the output is added and also normalized. And also remember there's a skip connection to it. You might have seen the skip connection earlier in ResNet kind of architectures. So that's how it is. And then the next layer is simple feed forward network, feed forward layer. And then again, the same thing, add and norm, addition and normalization. And here also there's a skip connection. And then this output of this will go into a similar stack like this. And this whole thing is happens 6 times. Okay. And then the final output of this, of all these 6 layers goes into the decoder stack. Okay. Now this, we'll talk about the whole decoder stack in the next video. I hope you guys understood the encoder stack and all these things which I've talked about, the input embeddings, how does it happen, and the position encoding. We are going to have a deep dive into it. And let me tell you beforehand, this people directly jump into using BERT model. I know Hugging Face provides a very good API and a very good interface of using this model wherein you don't even need to understand what's happening with it. But there are certain things which if you don't understand or if you don't know, like one of the thing I would tell that I've seen people perform doing the mistake that there is something called the model which was defined in the original paper and it is 512. What does that mean? Which means that every input embedding is the the dimension of it, or let's say the output of every real, okay, output of every layer. That is, the output of this can also will only be of dimension 512. Output of this will also be only of dimension 512, and this also will only be of dimension 512. And similarly will happen for all the layers. So what happens? Only a certain length of sentences can only be taken as input for processing for a BERT model, the original BERT model. However, there are multiple variants to it, but for the original BERT model, there is a certain length of sentence only that it will take as input. Because if the tokenization length goes beyond 512, it will not give you error, but it will give you a warning which says that there could be indexing issues. Okay, you can try this out and you'll see a warning which would say that there could be indexing issues because the length of the tokens are greater than 500. Okay, so there are certain things, and why is this kept as 512? How this even pans out in the whole picture? So understanding these things is really important if you want to put the idea of solving any problem that comes in, and you know what are the problems that could you could face during that thing. Okay. So it's very important to deep dive into this network. So this was the encoder part of it. The decoder part we'll talk about in the next video. Happy learning.